Today we study Newton's law of universal gravitation. We first define gravitational field. We learned that the gravitational force is proportional to the distance squared between two massive objects. So if we consider the gravitational force applied to an object with a small mass with a small m, with another particle with the mass capital M separated with the distance r is proportional to 1 over r squared and product of the two masses. And there is a proportional constant that is called the constant of universal gravity, and it is directed toward the other particle. So if we define the unit radial vector from this source mass to the test mass, the unit vector, the direction is opposite to that unit vector because it is an attractive force. We can rewrite this one as a product of mass of the test particle with the gravitational acceleration. In that case, the gravitational acceleration is called the gravitational field, that is G capital M over r squared er hat. The small m is now scaled out. If it is the case, this is the gravitational force, the corresponding gravitational potential. I mean, force is a negative value of the gradient of potential energy. So just like what we have done with the gravitational acceleration, that is a gravitational field, we divide this force by mass m to find out the gravitational field. Just like what we have done with this, we divide the potential energy by the test mass to find the potential. So potential, gravitational potential is defined to be the gravitational potential energy divided by the mass of the test particle. Okay, because gravitational force is minus the gradient of potential energy, and the potential energy is minus g capital M and minus the gradient. So minus minus becomes plus. The gradient gmm over r is the gravitational force, and we can rescale with the gravitational field multiplied by the test mass. So we divide everything with by small m. So this is the gravitational potential. So this is gravitational potential. So minus cancel, and the gradient 1 over r multiplied by gm is the gravitational field due to a point particle of capital mass m at the origin. We know the gravitational field is gm, this one. We can make use of chain rule, and we find it is a function of radius r only. So this gradient can be effectively written in this form. The angle theta and phi dependence disappears in the derivative. So gradient operator applied to a function of a radius r only can be written in this form. So gm er hat 1 over r. That is minus r squared er hat. Oh, this is the gravitational field, gravitational acceleration due to the point mass capital M placed at the origin. Why don't we apply this result to consider the divergence theorem? Because G is Gm gradient 1 over r. What happens to the divergence? Divergence of a gravitational field is a Gm divergence of a gradient of 1 over r. Divergence of a gradient is denoted by del square, just like what we usually do for the scalar product between identical vector is denoted by a vector square. And explicitly, this del square is E1 hat x1 plus E2 hat x2 derivative and E3 hat x3 derivative dot the same thing. Because the scalar product applies only to the same kind of thing, I mean EI hat dot EJ hat should be chronicle delta IJ, and it is either 1 for I equals J equals J, I equals J, and 0 for I equals not equal to J. The answer is x double derivative, y double derivative, and z double derivative sum. Okay, so let us compute this one. So 1 over r is one over r. X derivative is chain rule, and this is this. So it is r cube x over r cube. If I take another derivative, x over r cube, then it is just 1 over r cube, and then plus x 1 over r cube, so 1 over r cube, and this is minus 3 r to the 4th power, and that is x over r, and wait a second, x is missing, x, so x is 1 over r cube minus 3x squared over r to the 5th power. So if I make use of this. This result is 1 over r cubed 3x squared r fifth, 1 over r cubed 3y squared over r fifth, 1 over r cubed minus 3z squared over r to the fifth power. If I sum everything all together, it's a 3r cubed minus 3r squared over r to the fifth power. So this is 1 over r cubed and it is exactly 0. Note that this derivative exists only if r is not equal to 0. So what we have obtained is, if I compute the divergence of the gravitational field, the answer is 0 for r is not equal to 0. Therefore, we record that Kepler M is placed at the origin. Therefore, except for this point, everywhere else, there's nothing. It's a vacuum. So in free space, gradient of G, gravitational field, is vanishing. However, we were not able to evaluate the divergence of the gravitational field at r goes to 0. That's the problem. What we want to do is we make use of the divergence theorem. Divergence theorem shows the volume integral of divergence over a space V is always expressed as the gravitational field multiplied by the infinitesimal vector element, area element, as a scalar product over this closed surface that encloses the whole volume V. So this surface is the boundary of this volume V. Therefore, we can evaluate this integral on the surface. We had the problem of evaluating integrand as r goes to 0. However, this right side can be evaluated because the radius is usually finite, and why don't we take the volume to be a sphere of a radius r and centered at the origin. If it is the case, there's a sphere, Kepler M is placed in here, we have a radius, and there is a small patch of area element. Area d sigma is used, we can use the spherical polar coordinate to identify the position with the theta and phi. This arc length is r d theta, and this arc length is r sine theta d theta. And there's a normal direction n hat, so this sigma equals n hat multiplied by this area r squared d cosine theta d phi. This is the area element vector, and this n hat is actually er hat, and er hat is written in the form. Okay, in the gravitational field is G capital M r squared er hat. Therefore, we can evaluate the G dot this sigma to be, here r squared cancels, and we have negative side gm, and ER equals 1, we have d cosine theta d phi. This integral over a closed surface of a sphere of radius r centered at the origin. Okay, so right hand side is integrable. The evaluation of integral depends on the azimuthal angle, and polar angle integral is 2. So multiplied by these two numbers, we have 4 pi of the solid angle. As a result, we obtain this identity called Gauss law. Gravitational field flux, just like what we learned J dot is sigma over a closed surface. It was divergence J, and this was the amount of mass coming out of the surface. Therefore, per unit time, therefore it was the time rate of decreasing the mass inside the surface, that is called V. This was the continuity equation. Just like what we have done, this is a flux or current. So this is a flux. What flux? Gravitational flux. Gravitational field multiplied by area vector as a scalar problem. So that is proportional to mass inside that volume, that closed surface. And proportional constant is 4 pi g. G is the strength of the gravitational force called gravitational constant. So we have arrived at the Gauss law in the integral form. And we know that this mass is contained inside the surface, so it is a minus 4 pi g and density and volume integral. If we apply the divergence theorem, it is divergence of the gravitational field, volume integral, and two volume integral. They are the same. We can combine these two, and we have divergence g plus 4 pi g rho integrated over the volume. So if we take it, because it is always a zero, regardless of choice of the volume, we can take a very small tiny volume centered at some point x0 with the radius epsilon, and epsilon goes to 0 plus. So if we decrease this epsilon, it is not 0. Not at all, it is not 0, but it is approaching 0. Then this integrand is frozen to a fixed value. So at constant evaluated x equals x0. So the integrand can be pulled out of the integral. And then let me put a subscript epsilon to denote this volume is very tiny in this limit equals 0. It approaches 0, however, it is non-zero. So I can divide this one. Finally, this integrand vanishes. The resultant equation is called the Gauss law for differential form. Previously, we were using the integral form. So differential form of the Gauss law is like that. And this is also true for the electrostatic case. Electrostatic force, according to Coulomb's law, is 1 over 4 pi epsilon 0 r squared qq. These are electric charges, and unit vector. That is, if the two charges are positive, it is a repulsive force. Gravitational force is minus g mm r squared er. They are very similar except for the coefficients and strength, weight, this mass and charge. We rescale this one with the test charge, then we obtain the electric field. The gravitational field obtained by dividing this by test mass, and the answer is 1 over 4 pi epsilon 0 q over r squared er hat, and it was a minus g capital M over r squared er hat. They are identical to each other except for the replacement. Gm minus Gm. And this, in the volume integral, it is to be replaced with the rho and minus G rho. So minus G rho is to be replaced with the 4 pi epsilon 0. So because we have 4 pi rho over epsilon 0, equivalence is 4 pi G rho. So minus 4 pi G rho is to be replaced with rho over epsilon 0 in the electrostatic case. That's the reason why we have the same equation with a different normalization. This is the gravitational field and this is the electric field. They both satisfy the Gauss law. In addition, the mass is positive definite, so Gauss law works, and this represents the mass inside the volume. And if we consider Gauss law for the electrostatic field, then it is related to the charge contained inside this volume. And what about the magnetic field? Magnetic field is composed of north and south pole, and they are dipole. Even though we break a magnet into two pieces, it is not a monopole, but it becomes another dipole. So it is impossible to separate the north and south poles within a single magnet. And even though you break it down, every piece of magnet becomes magnet again. So the total sum of north and south pole is vanishing for in any space. That's the reason why the density is if one integrate it over a space, it becomes a charge, it becomes a mass. The magnetic charge does not net charge does not exist. So hence the differential form of the magnetic field's Gauss law vanishes. This is the realization of the non-existence of magnetic monopole in nature. We can consider the gravitational potential energy by multiplying the test mass. So this is the gravitational potential energy between two particles. And when there are three particles, the gravitational potential energy can be computed using this way. So first, let the three objects are all very far to the infinity, and then bring one at some point at the origin, for example, and bring the other another one, and remaining piece to come in this position. And the distance between 1, 2, 3 objects R1, 2, R2, 3, and R3, 1. Then the final result will be like that. If you do the integral, you will find exactly the same result, assuming that at infinities the total potential energy is set to be 0 at all of the three massive objects are far from any other. So finally, we are ready to attack the problem, Kepler's law. Okay, so this is according to the central force, that is a gravitational force. For simplicity, we consider two-body problem, and the masses are m1 and m2, and gravitational potential energy of this system is in this form, where K is the gm1, m2. We introduced the distance r, that is the distance between the two objects. So this is a very nice coordinate. So this is relative coordinate. Relative coordinate is defined by the x1 minus x2 magnitude. At the center of mass frame, the total kinetic energy is PCM squared plus 2 mu p squared, remember. And this small p is the small p vector, is the velocity of this relative coordinate multiplied by mass, that is this one. Instead of m1 or m2, it is reduced mass. That's quite important, very, very important for two-body system. At the Cm, this one disappears, and the only kinetic energy is internal kinetic energy, that is always described by this. And remember, P equals mu r beta dot. That's quite important. Because at the center of mass is xcm, m1 x1, m2 x2, divided by m1 plus m2. We set this one to be 0. At the center of mass frame, this one vanishes. So numerator vanishes. And we have a relative coordinate. Relative coordinate is x1 minus x2. And we use the unit radial vector connecting the two lines. So, for example, E1 hat, M1, M2, E1 hat. So ER, radial direction. And the distance is R, so this is a linear equation. So origin is at the center of mass. At the origin, the two particles are on a straight line and they are opposite direction. And distance from the center of mass to each object is a crust, m2, m1. The ratio of the two masses, inverse ratio, reciprocal ratio of the two masses will be the distance from the center of mass to each particle. So the answer is this at the center of mass. We can check x1 multiplied by m1, that is m1, m1, x2 multiplied by m2, m2. So if we sum these two, the magnitude is the same, sign is opposite, so vanishes. Okay? So if we subtract x1 subtracted by x2, then this negative sign becomes a positive sign. Sum will be r, er. So it's correct. So this is the answer. Let us write down this total kinetic energy at the CM frame. That is internal kinetic energy. Internal kinetic energy in this frame is just the sum of the kinetic energy of each particle, and we substitute these values in it. And along this, we have r, er hat. This time derivative is r dot er hat plus r er dot. And we remember er dot is equals er hat plus r theta dot, e theta. The tangential component of the velocity and radial component of velocity. And we know er dot, e theta, they are always perpendicular to each other. Therefore, the velocity squared is r dot squared plus r theta dot squared. This is r dot squared. Velocity squared is this. And the mass, what is the mass? This two-body system has mass of reduced mass. That is a product of the two masses divided by sum of the two masses. How can I know that? I have substituted these numbers in it. Alright, next we consider orbital angular momentum of the two particle state. This is the position x1 cross p1, x2 cross p2, and p1 equals m1 x1 dot, p2 equals m2 x2 dot. Okay, I made use of this to find the derivative m1 multiplied, so m1 m2, this is reduced mass mu, and dot is radial and tangential, and x2 is here, and we have negative sign on it, but x2 dot also has the negative sign on it, so minus minus squared is a positive sign, and we have x2, that is m1 over m1 plus m2 are copied, and then multiplied by m2 x2 dot m2, so m1 m2 is still reduced mass. Now we compute the cross product. Er cross er must vanish, so I don't need this one. So er cross er vanishes. I don't need this one. What I need is only this. And then er cross e theta, er hat cross e theta, that is e3 hat, we know very well. And this is mu, and this one. If we sum, this is 1. And we have a factor of r. So r squared theta dot, mu r squared theta dot, e3 hat is the total orbital angular momentum. Alright, total mechanical energy is the sum of the potential energy and kinetic energy. But kinetic energy, there is a missing term. What is that? That is the kinetic energy due to the tangential motion. Tangential motion has 1/2 mu r theta dot square. This is this one. However, what's that? Mu r theta dot. mu r squared theta dot is L. That is a constant of motion. This is orbital angular momentum. That is a constant of motion. Why? Because it is a central force. Any system of particles has the vanishing orbital angular momentum and vanishing torque due to the internal force, internal torque. Therefore, it is constant. Then I can replace r here, r squared theta dot r theta dot total square. So why don't we square this one? So mu r theta dot L. Then r theta dot equals L over mu r, right? L over mu r. So 1/2 mu L over mu r squared. The answer is 1/2 mu L squared. Aha, this one. 2 mu r is here, r squared. 2 mu r squared. This one is actually the kinetic energy along the tangential direction. But the angular time derivative theta dot is always expressed in terms of radius because the orbital angular momentum is conserved. Because of that, I can allocate this tangential component of the kinetic energy into the effective potential for the radius. It is actually, this is the correct potential, but I don't need this one in the angle because the angle variable has been disappeared due to the conservation of orbital angular momentum. Therefore, I redefine the potential to be effective potential. Okay, that's it. So total mechanical energy is now sum of radial kinetic energy plus effective potential. And effective potential is the sum of the potential. It's a sum of potential plus radial kinetic energy. That is expressed in terms of radius only because L, the orbital angular momentum, is conserved. Now the conservation of mechanical energy, that is the energy formula, in combination with orbital angular momentum conservation, I have reached it. This angular momentum is a constant. So this constant means that as well as the magnitude, the direction is also fixed. Therefore, the two-body orbit is always on a single plane, that is xy plane. Right now the angular momentum is along the z-axis. Alright, so it is just like one-dimensional problem, even though it is two-dimensional problem, because the angle dependence is completely explained in terms of a constant, and it is expressed in terms of the radius. So we have only a single variable, even though the actual motion is on a plane that is two-dimensional. We have collapsed this problem into a one-dimensional problem. That's the reason why we say this. Actually, this is not a potential energy, but effective potential energy. But in one-dimensional problem, we have originally the potential energy is diverging to minus infinity as r goes to 0. However, because of the 1 over r squared term in the tangential component of the kinetic energy, that is a positive definite. So it wins the game as it approaches r goes to 0. So it is a modified form of the U effective has a local minimum, and actually there's a global minimum. So we have radius and the effective potential that has a minimum, and physical region is just above this. If it is below that, then it is impossible to have an orbit, and it will just decay. It will just decay. The strong attractive force do not allow to have them move along an orbit, and they just collapse to a single particle. Instead, at this point, there is only a single point allowed, that is a circular motion. If we increase the total energy, the physical range will be over there. That means the minimum radius and the maximum radius appears. Oh, this is related to the elliptic orbit. And then, if we further increase the energy, you still notice that as r goes to infinity, we have potential energy k over r that is still negative, but it approaches a zero as r goes to infinity. However, the tangential component of the kinetic energy is fastly decaying because 1 over r squared is much smaller than 1 over r as r goes to infinity. So we don't need this term as r goes to infinity. So if the total mechanical energy reaches zero, that means the particle do not have any kinetic moment, kinetic energy as r goes to infinity. That is barely leaving out of the orbit. That is called the parabolic orbit. So it's escape velocity. If you have it just exactly same as escape velocity, we can escape from the orbit of the two particles' gravitational force. If we further increase the energy, then it becomes a free particle, and there is no upper limit of the radius. So it would diverge. So the orbit is not periodic anymore, and it will go very far away. So in that case, it is a hyperbolic orbit. And first of all, Kepler has found that the orbit is elliptical if it is localized, not based on this physical theory of a Newtonian gravitational force, but based on the observation. And actually, Kepler did not observe, and Kepler assisted Tycho Brahe, and who observed with his bare eyes. So many data were collected accurately, but he was not able to analyze this data. But Kepler was able to analyze the data to show the orbit is elliptical orbit. And at the end, the Newton's law of motion and the Newton's law of gravitational force that shows the inverse square law allows the conic section orbit. Conic section orbit. But right now I have shown every kind of allowed orbit. This is a circular orbit, minimum energy. If the energy increases, it ranges from moving around the minimum radius and maximum radius, that is elliptic orbit, and then it barely leave the attractive force due to the gravitational force that is called the parabolic orbit, and it is a completely free particle in that it is called the hyperbolic orbit. Kepler's first law is law of orbit. What he has found was planet's orbit is ellipse. However, as I already explained, ellipse is a general general orbit for the bounded system. Bounded means it is oscillating between the R minimum and R maximum. And there are a special case is the circular orbit when R minimum is equal to R maximum. When we increase the energy to have the energy equals exactly 0, then it becomes a parabolic motion. And in addition, if we increase the energy further to the positive value, we arrive at a hyperbolic orbit. Interesting, it is very interesting that these orbits are all expressed in terms of a cone. There's a conic section. You cut a cone, it's a parallel to the bottom, a base. It is just a circle. The circular orbit is a cut of this form. An elliptic orbit can be obtained by cutting the cone with a slightly with some slope with respect to the horizontal plane. And if we increase the slope to reach the point where the slope is the same as this line, then it becomes a parabola. And you increase the slope further to the perpendicular to the base, then you will find the hyperbolic orbit. It is you can find it as a straight approaches the straight line. And if we make use of energy and angular momentum, here this alpha is called the semi-lattice rectum, and this alpha is determined by the angular momentum, and this is eccentricity that discriminates the four classes of curves. This is for the positive, energy is positive, all vectors are positive, so it becomes a greater than 1. So epsilon is a greater than 1 for hyperbola. For parabola, energy is a 0, so epsilon eccentricity is exactly 1. For the two states, these are bounded system. Bounded system is allowed only if the total mechanical energy is a negative. Therefore, it is less than 1 after square root. And then it cannot decrease further less than 1. So that when it becomes a minus 1, the whole value becomes a 0. That is the minimum energy. At the minimum energy, it is called the radius is the same as a semi-lattice rectum. Okay, that is the circular orbit. All of these results are based on the conservation of angular momentum and conservation of total mechanical energy. Two constraints, especially if we consider the conservation of orbital angular momentum, it leads to the law of areas, that is Kepler's second law. And it is due to the conservation of orbital angular momentum. And if we write this one in this form, integrate out with respect to time, then what we find is the orbital angular momentum that is conserved. And theta dot is the theta over dt. We can rewrite this as this form. The area, if we have divided this reduced mass, the area, radius, angle d theta, this is an arc. The area of this sector is 1/2 r squared d theta. Therefore, if I make use of this and this, it is expressed in terms of constant as the orbital angular momentum divided by 2 mu. So time is proportional to the area, this area of the sector. That is called law of areas. The third law of Kepler's third law is a law of period. And law of period, we can make use of the way what we have used when we derived the solution for the simple harmonic oscillator. We made use of the fact that energy conservation. From energy conservation, we have found the velocity and divided into 4 pieces. This kind of oscillation, we cut it for 1/4 of period and express this one as an integral of arc sine. It is exactly the same, and this one is the same, follows the same approach to find the orbit and find the trajectory of the simple harmonic oscillator with arc sine, and this is also the arc sine integral. And the result is this one. Here, r is the relative coordinate. That means the distance between the two particles. R is the absolute value of the relative displacement. Therefore, if, for example, an object is very heavy like sun, and the other object is much lighter, so sun is fixed at some point, they make an orbit, and this is a minimum value of the radius, minimum value of this relative coordinate, and this is maximum value of the relative coordinate, and we call this is not the center, this is but a focus. A heavier object place is focus, but it is not always true. It is not fixed. For example, if they are identical particles, center of mass is fixed and both of them are moving. So this figure does not show the inertial reference frame. This one just to show the relative coordinate. Relative coordinate. So in this case, two objects are here. Somewhere around here there is a center of mass, and the still center of mass is moving in this figure. But for simplicity, we fixed a particle at the focus, and in that case the radius appears and the polar angle appears in here. In this coordinate there is a center, the origin of this axis. However, the r is not measured from the origin but from a particle to another particle, and a particle is at the focus, not at the origin. That's quite important. So this theta r, they are measured from focus. That's very important. It's not coming from, measured from with respect to the center. And center of mass is still moving in this reference frame. All right. Anyway, we have alpha. Alpha is a semi-lattice rectangle. That is the radius of a circle, the only single point radius of the orbit for the circular orbit. And we have eccentricity that is determined by the energy and angular momentum. This is a typical example for the elliptic orbit, and you can just follow the geometry of this. And finally, the third law relates the period. Here I wrote tau as a period, it's not tension. Period square is proportional to the semi-major axis cubic. So semi-major, A is a semi-major axis, this is a semi-major axis, and this is a semi-minor axis. Okay, the period square is proportional to the cubic term of the semi-major axis. And this is obtained by integration, and you might want to evaluate this integral, quite interesting integral. So it is a very, very mysterious formula. So Kepler named this one as a harmonic law of planetary motion. So this is a decisive triumph of Newtonian mechanics. We have solved the special case for the circular orbit, and please follow the calculation. Another important point when we study gravity is that there are two different masses involved. The F equals ma. In F equals ma, we have inertial mass that distinguishes the motion, the acceleration of a particle due to the force. But the origin of the force in the gravitational force is the mass that is not inertial mass but a gravitational mass. So in general, the gravitational mass and the inertial mass does not have to be the same. Nobody knows why. But Einstein noticed that this is a fundamental postulate. This can be a fundamental postulate of physics. Nobody knows, however, it is by accident or anyway, the two masses are the same. Because of this, the gravitational force is closely related to the geometry of space in nature. Okay, that is quite distinguishable from any other fundamental forces that are described by quantum field theory. But still, we do not have a correct theory to describe the gravitation in terms of quantum field theory. The main reason is that the gravity governs the geometry of space. Anyway, as well as this is called the general relativity's equivalence principle, that the inertial mass and gravitational mass are the same. This is equivalence principle. Anyway, as well as the general relativity and the special theory of relativity, that the speed of light is the maximum speed of a massive object, and speed of light is the same for everyone. So due to that fact, everything changes in the limit v approaches the speed of light, and in everyday life, it has a very strong consequence. I mean, everybody uses GPS, geo-positioning system. Without understanding both the special and general relativity, one cannot commercialize the GPS, because every day, the error accumulates more than 10 kilometers per day. We have to understand relativity and apply it. It is impossible to make use of GPS if it produces error by 10 kilometers every day. But because we correctly understand what general relativity is and the special relativity is, it is realized to be commercialized. It's a very interesting fact. So you can apply what you learned in high school for the analytic geometry that is closely related to the conic section, and this is a quite good example to understand why. Okay, that's it for today. Thank you.